conference. The conference is just being recorded now, and it's a pleasure to start this afternoon with R.Monteiro from Queen Mary University of London. I think it was Queen Mary College, maybe some years ago.
In the past, yeah.
In the past, yeah. He will talk about double copy of amplitudes and of classical solutions. So thank you. Floor is all yours.
Well, thank you, Massimo. Well, first I want to thank the organizers for the invitation. So I was asked to give an overview on work on the classical double copy. So I'll discuss, the title is Double Copy of Amplitudes and of Classical Solutions. Now, the double copy is a relationship between gauge theory and gravity, which is a perturbative relationship, but in some instances can be extended to exact solutions, as I will describe. Now, this is the outline. I will first give a general introduction to the double copy, then I'll talk about how these ideas fit into the framework of classical solutions. How do they relate classical solutions in gauge theory and gravity? And then I will justify why that is the same as the double copy for scattering amplitudes. And finally, I will just very briefly, it was not part of the topic that I was asked to talk about, but it's a very recent work, and I will mention briefly some application of similar ideas to string theory amplitudes. Okay, so, well, what is the motivation to look at gravity in a new way? Well, perturbative gravity is pretty hard. If you look at the Einstein-Hilbert Lagrangian and you expand in the graviton fields, you get an infinite number of vertices. Unlike, say, the gauge theory case, where you have at most a 4-point vertex. Of course, at a given order in perturbation theory, you only need a finite number of vertices. But still, yeah, as you go higher in your orders, you need more and more vertices, and they look much more complicated than in gauge theory. So, for instance, here, this figure is taken from an old paper by DeWitt, and if you hear some momenta p, p prime, and some and the metric, and there are a bunch of indices, and this p6 symbol represents 6 permutations of indices, and there's a further symmetrization in indices. So there are many terms here, I think more than 100, and this is the 4 points, and so you see where it goes. There's a p24 here, 24 terms. So this motivated, I mean, people use this to make actual calculations and important calculations, but certainly there was a need for something more practical to move forward. And that was the main motivation for this relationship of gravity as a double copy of gauge theory. Let's think about scattering amplitudes, which we think about as natural perturbative quantities. So for scattering amplitudes, you have some asymptotic states in or out. And for Yang-Mills theory, those states are gluons. You have some plane wave with some null momentum, you have some polarization vector, you have some Lie algebra elements. And this polarization vector lives in a space with d-2 dimensions, where d is the space-time dimension. So say in 4 dimensions, you have 2 polarizations, 2 physical polarizations. Now, consider a tensor states given by of this type, given by the tensor products of 2 polarization vectors. Well, if you consider all such states, they span all the polarizations, all the tensorial polarizations, and these states correspond to the 0 mass level of the string. They can admit a graviton component, but also a dilaton component, which would be the trace part. So the graviton would be the traceless symmetric part, the dilaton would be the trace part, and the B field would be the anti-symmetric part. And well, if you have d minus 2 degrees of freedom here, then you have d minus 2 squared in the gravity case. So in 4 dimensions, it would be the 2 polarizations of the graviton, but also the dilaton and the single degree of freedom of the B field in 4 dimensions, which you can think of as the axion. Okay, so when you then look at scattering amplitudes, what is quite non-trivial is that this factorization, if you look at gravity states of this factorizable type, which form a basis for general ones, there are ways of writing the scattering amplitudes that exhibit this factorization. So you get formulas of this type where the amplitude for the gravity states is given by the products of gauge theory amplitudes for the gluons with the left polarization or the right polarization. Then you have to strip off the color. There's some color in gravity, and you also have to correct the propagator structure with some inverse propagators. So this is just a schematic formula. There are different ways of realizing this formula, both at tree level and at loop level, as I will mention. Now, I chose here these very simple kind of states, but you could have states, let's say, in a supersymmetric gauge theory, in a different supersymmetric or not gauge theory with different degrees of supersymmetry, and then you get corresponding supersymmetry. So the sum of its supersymmetries in a gravity case, for instance, n equals 4 super mills and n equals 4 super mills, giving an amplitude in n equals 8 supergravity. At loop level, this works at the level of the loop integrands. A famous application of that is the study of the supergravity behavior, of the ultraviolet behavior of supergravity theories. So in the 80s, people thought any 4-dimensional supergravity would diverge starting at 3 loops, but that's not the case. In fact, up to 5 loops at least, it does not diverge. Most people think that it starts diverging at 7 loops, but it would be nice to check that, which is conceivable only because of this kind of tool. Right, now the origin of the double copy actually lies in string theory. So there's a very different way of thinking about perturbative field theory as being the limit of string theory as you send the string length or its square alpha prime to 0. That gives a picture that looks very different from the usual picture we have as scattering in terms of Feynman diagrams. Instead, we have one world sheet. So this will be the string states, in the case of the closed strings, some closed strings here. And on this world sheet leaves a 2-dimensional conformal field theory. You can turn a calculation then of the scattering amplitudes into a correlation function of vertex operators that represent the external states, in this case on the sphere at tree level. And in addition, then you need to integrate over the moduli space, which means integrating over the positions of these vertex operators on the sphere. Now, this gives a global view of the expression. Instead of having many different diagrams, at the given order in perturbation theory, you get a single diagram. In this case, at tree level, genus 0, you get a sphere. And so this is good to look at some global properties of the amplitude, and these techniques of 2D CFT, basically just complex analysis, give you a lot of powerful tools. One insight from this has been the relation between the scattering of gravity states and gauge theory states seen as the low energy limits of the scattering of closed strings and open strings. So these vertex operators are representing the asymptotic states. For closed strings, they look like the product of ones for open strings. For instance, for the 0 mass level of the string, for states of this factorizable type, the vertex operators look a bit like the products of vertex operators for open strings for the left side which is actually related to the left moving sector of the closed string, and for the epsilon tilde, which is related to the right moving sector. Then when you calculate the scattering amplitudes, so this was worked out in a beautiful paper long ago by Kawai, Leland, and Tai. You do a correlation function of the vertex operators and you integrate over the moduli space the locations of the vertex operators on the closed string side. That's a two-dimensional integration. And what they worked out is how to disentangle that into two independent integrals, one-dimensional integrals, which then will be associated to disk integrals corresponding to open strings. And then you get the scattering amplitude for gravity, which looks like a sum of products with some phases, and these products are the products of two gauge theory amplitudes. And so in this sense, then you have, let's say, the scattering of closed strings as the double copy of the scattering of open strings, and in the field theory limits, you get gravity as a double copy of gauge theory. And there are different ways then of seeing this from the field theory perspective. There's the KLT way, which is just taking the KLT relations and taking the field theory limit. There's a diagrammatic way put forward by Byrne, Carrasco, and Johansson, based on something called the color kinematics duality. And there are also some worldsheet kind of story just for field theory, put forward by Cachazo, He, and Yuan. And yeah, so there are many different ways of thinking about it. Right, so why simpler? Let me just give you a very pedestrian view. So let's think about just 3-point interactions in terms of the 3-point vertex. It's not really how you then want to think about it generally, but it's just a very simple setting where you can see the simplicity. So the 3-point vertex in Young's theory, you can check your textbook, looks like this. There's a color part of the vertex, and there's a kinematic part of the vertex. Now, if you write your gravity theory in a double copy-like way, then you'll be dealing with a compositive field, sometimes called the fat graviton, where you can put together the graviton, the dilaton, and the B fields, or you can just forget about the dilaton and the B fields. And the 3-point vertex looks like this if you write it in terms of this field. So, and what you can see here is that the n primes and the prime indices don't talk to each other. So they are the left and right indices here, which is a reflection from the string theory perspective of left moving sector and right moving sector. So there is a reduction of the tensorial structures, because you can, generally in Einstein Hilbert Lagrangian, you get mixed tensorial structures with these indices, but here they are factorized, which gives a much simpler 3-point vertex. And then as you go higher in perturbation theory, the simplification becomes more dramatic. A powerful implementation of this idea is the color kinematics duality, which I want to describe here. It's not the focus of this talk, but it's certainly one of the most fundamental structures in this double copy story. Okay. Now, beyond scattering amplitudes, and now also using scattering amplitudes, and another important application of perturbative gravity, in fact, more widely known than the supergravity story I told you about, is looking at gravitational phenomenology, for instance, gravitational waves, now observed by LIGO. And there has been a lot of work on trying to import these techniques from quantum field theory into classical field theory. So there are older and newer efforts to write a double copy-like field theory for gravity. There is a new and rapidly growing fields of using actually scattering amplitudes and taking their classical limits in order to obtain classical physics, and in that way reformulate gravitational perturbation theory. And the advantage of that is that scattering amplitudes are gauge invariants, so they don't depend on some choice of coordinates, and in that way they're very simple objects, and they are optimal for perturbation theory, at least in the relativistic setting. And so if you have scattering amplitudes in gravity, then in your classical physics, you can relate them to scattering amplitudes in gauge theory via the double copy. And the gauge theory ones are easier to calculate, so you can import those results for gravity. There is also new work on discussing amplitudes or quantities similar to sketching amplitudes on different space-time backgrounds. So not Minkowski, but say a gravitational plane wave or ADS or DS. And well, one highlight of these applications of the double copy that I should perhaps mention has been more like in line with this story, has been the revolution in the post-Minkowskian approach to general relativity, where new corrections to the two-body potential were calculated to much higher orders that were thought possible only a few years ago. So this is a third post-Minkowskian, which is just perturbation theory in G Newton. So G Newton to cube, G Newton to the fourth. Okay, now I'll be talking here about the different aspect of this story. So if you say that gravity is a double copy of gauge theory, well, let's think what are the basic objects that we think about when we think about gravity. Well, black holes are the most characteristic objects in gravity. And then you can ask, is the black hole a double copy of something? Well, if you start thinking about it, it's a bit confusing because the double copy is a perturbative story. So, and it is based on a graviton field or this fat graviton. But let's just think about pure general relativity as a graviton field, which you then want to see as a double copy of some gauge field. But if I just give you some metric, there's no natural way of splitting Minkowski plus graviton. In fact, that does make sense for certain manifolds. So yeah, how do you separate Minkowski part of the metric from the graviton part of the metric in the cases where that makes sense in a geometrically meaningful way? The other issue is that double copy is a perturbative story. So, well, if you want to think now about a black hole, well, that looks very non-perturbative. So, at least naively. So, well, you may think about considering expanding your solution in G Newton, so order by order in perturbation theory, and how double copy works for sketching amplitudes. The way you would apply it is that you would apply it order by order in perturbation theory. And then you would have to sum over all those orders and hope to get something that looks like a double copy, which sounds like some kind of miracle would be necessary. Still, yeah, you can get your hands dirty with some basic examples in perturbation theory, such as Schwarzschild solution or shockwave solution. And I just mentioned a few works more or less in this context of constructing the solutions perturbatively. Or you can even hope for a direct map of exact solutions, but some kind of miracle seems to be necessary. And that miracle, as often, is provided by symmetry. So this will be the focus here in this part of my talk. You can consider a class of spacetimes called Kershfield spacetimes that look like exact perturbations of a base spacetime, which here for my example, I will consider to be Minkowski spacetime. So it's like Minkowski plus some graviton field, where this K is null and geodesic with respect to the null, to the Minkowski metric, and therefore you can show also with respect to the curved metric. In fact, you can raise the index with any of them. The Einstein equations actually linearize. First, the inverse metric just truncates because K is null, and the Einstein tensor with 1 in x up, 1 in x down actually takes this very nice linearized form. So this is a dressing simplification, which actually lies at, it underlies a lot of developments in finding black hole solutions, starting from Kerr, where there was something related to this, to its higher dimensional extensions, where there's something exactly like this. Well, I mean, the procedure used to construct the higher dimensional generalization of Kerr was precisely based on the assumption of being Kershfield spacetime, and so on. So important solutions are of this type, and in particularly important stationary solutions, such as the one I mentioned. Now, in this case, so if you take the time component of this k to be 1, and if it's not, you just shove that into phi, just rescale k, then the time and the space-time components of the Einstein equations in vacuum just take this form. And well, what does this tell us then? What are the clues here to obtain a gauge field whose double copy would be this gravity solution? There's a very natural candidate for a single copy as opposed to double copy. So if this linearizes the Einstein equations, well, it should linearize the Engels equations, must be an abelian solution, so you can just trivialize the color. Or I mean, you can just get rid of it, or just have a constant color vector, which is the same. Then if this is a double copy of the k, then you just put 1k. However, in the sketching amplitude story, you don't square the propagators. There was this inverse propagator that I mentioned in this schematic formula for sketching amplitudes. So you just keep this phi, which is a kind of spatial propagator because it satisfies this Laplace equation. And you plug that into the Engels equations, and you get actually precisely these components of the Einstein equations. So let's check this in an example. The case of a point mass and a point charge. Well, the case of a point mass, its understanding in GR as an exact solution is Schwarzschild solution, which can be put in the Kerrschild form. So here the time coordinate is not the same as the ordinary Schwarzschild time coordinates. And you can see that these are not static coordinates. And in gauge theory, well, the point charge will be the Coulomb solution, which can be written in this way, in a slightly different gauge than the one that you would normally write it in. So in this sense, the Schwarzschild solution is a double copy of the Coulomb solution, and you understand that as somehow decomposing the solution into the trivial metric plus the graviton fields, which is then the double copy of the gauge theory solution. And then you can move on to more complicated cases, but somehow this decomposition is what this Kerrschild story is giving us, is giving a geometrically meaningful way of making this splitting. You can consider rotation, occur black hole. You can go to higher dimensions, the Myers-Briggs black holes, which have more rotation parameters. They generalize the Kerr solution. There are other classes of higher dimensional black holes, such as black rings, which are known exactly in 5 dimensions and approximately or numerically in higher dimensions. They are known not to be of Kerrschild form, and so it's actually not known how to interpret them as a double copy. It would be interesting to see how that works. Well, the analog of a cosmological constant is a constant charge density, as you might expect. There's an analog also with the net charge, which is a magnetic monopole charge. So this is also a natural connection, but here, in terms of the story of the Kerrschild double copy, just an exact map. You can just take your, let's say, your tau net solution, which has a mass-like parameter, and your net charge, and it's of the double Kerrschild form and multi-Kerrschild in higher dimensions. And single copy is a dion where this bit, which is somehow the single copy of this one, represents the electric charge, and this one, the magnetic monopole charge. Then you can consider some space-times with radiation and check that the double copy makes sense also between gravity and gauge theory. Okay, and there is a lot of related work here, which yeah, I can't really do justice to it. Let me tell you though the following points. So I told you that the double copy of Coulomb was Schwarzschild, but I've also told you before that the double copy of Engels theory is actually this theory where you have not just the graviton but the dilaton and the B fields. So how can the other ones arise? Well, a nice setting to look at this, and I will not describe it in detail, but I'll just describe to you in words, is double field theory. So double field theory is a version, a field theory that still has some properties inherited from string theory. So it's meant to keep some of the properties of string theory, in particular a version of T-duality. So what you do is that you double your geometry. So you have some coordinates x, your standard coordinates, which are conjugates to the usual momentum. But you also have some coordinates, if you want to think about them as auxiliary coordinates, some auxiliary coordinates that are conjugate to the winding. And T-duality exchanges momenta and winding, just mixes that as a linear transformation in general. And so you create a double geometry.
Ricardo.
Yes.
Sorry, Ricardo, just to test it out. I have a question.
Sure.
Do the coordinates that you obtain naturally with this decomposition and seem pretty rigid cover just the region outside the horizon of the black holes, or are they the maximal analytic extension or something in between?
Sorry, you mentioned the Herschel coordinates.
Sorry, Schwarzschild.
Yeah, in Schwarzschild, they are actually the ingoing or outgoing Eddington-Finkelstein coordinates. It depends which sign you choose here. You see, the coordinates are not static, so you know what sign you choose to put here between, in T. So because this then appears the T plus dr squared. Yeah, so they are related to those if you then transform U. So basically, this would be du or dv, and then it's the Eddington-Finkelstein coordinates.
Thank you.
Yeah. So okay. So here for this double field theory, I mean, you will have at least seen that. I can't really introduce it here in the archive, and you saw a double copy, so double, but these doubles look quite different because this is 2 copies of gauge theory, and this is just doubling the dimensionality of your space such that you can act on it in the same way that T-duality acts by mixing momenta and winding. But actually, they turn out to be connected, and in fact, so in double field theory, there's a generalized metric that mixes the metric and the B fields, actually the metric in the string frame, so also the dilaton, and then there's a DFT dilaton, which is related to the supergravity dilaton and the determinant of the metric. And yeah, so you can package these fields in some way where you can write a Herschel ansatz that extends one from general relativity to one that includes the dilaton and the B fields, and this was something by Cancun Lee, and then you can extend that also to the heterotic case and to consider a more general ansatz, and you can see that the story of the classical double copy then extends there too. And one important, so this gives some more examples, but there's an important insight from this, which is that in that case, it's actually clear that the gauge theory solutions that can appear are associated to the left moving modes and the right moving modes, which are combinations of these coordinates. So the ones that transform in an irreducible way with respect to T-duality are not the coordinates like this, are x minus x tilde or x plus x tilde. And these are associated from the way that is arises in string theory with left moving modes and right moving modes. And so this gives a KLT interpretation. So the KLT was like this decomposition between left moving and right moving, giving the 2 open string factors, giving the closed string. And so here also you get a left moving gauge solution and a right moving gauge solution, giving you a gravity solution. Okay. And it also shows another point, it just brings home another point, which is that the double copy is actually non-unique. So you can restrict it to the pure vacuum case, but you can also extend it. So the Yanis-Newman-Winnicourt solution is a spherically symmetric solution, which is asymptotically flat. And when the dilaton field, so there's a dilaton parameter, when it's 0, it's Schwarzschild, you have a black hole. When it's not 0, you actually have a naked singularity, because you can't just deform Schwarzschild by a scalar fields and still have a horizon due to the uniqueness theorems. But that can be interpreted, that more general solution with 2 parameters can be interpreted as a double copy of Coulomb. And well, why would you get 2 parameters? Well, even if you think about polarization states in the story I mentioned before, if you have 2 polarizations from gauge theory, you can take the symmetric products, the anti-symmetric products, or you can take the dot product times the metric. And so that corresponds precisely to the graviton, the B field, the dilaton. In this case, if you do the double copy of the Coulomb, because it's the same solution, there's no anti-symmetric part to the double copy. So then there is no B field. Okay. Now let me describe in a bit more detail another approach, which is based not on the fields themselves but on the curvatures, which at least at linearized level looks very natural because they're gauge invariants. And there's an obvious relation if you have some sort of plane wave fields that looks like this. So this looks like something that you would want to generalize. However, yeah, beyond linearized level, the symmetries of these objects are not so easy to accomplish, and also they're no longer gauge invariants. Still, well, you can try to proceed, and a convenient approach, which is less cumbersome than some space-time coordinates, is to some space-time indices, is to take a spinorial approach to general relativity. So let's focus in 4 dimensions, although you could do something similar in higher dimensions. The basic object is some spinorial Wilbein, which gives you the information about the metric. And well, also given the metric, you can get a normal tetrad, and then given the Pauli matrices, you can construct this object. And what it does is that you can translate space-time indices into spinorial indices. For instance, like this. This is something widely used in particle physics called the spinor helicity method, and widely used also in general relativity. And so what you're aiming for is some formula of this generic type, where some gravity curvature is like a double copy of the gauge theory curvature, with some mediated by some scalar, which here is just this plane wave factor. And in the sketching amplitudes formulas that I shown before, it was these inverse propagator factors. Right. So let's then think about the spinorial version of the curvature, and let me focus on the Weyl curvature. So let's just take the vacuum spacetimes for simplicity. This is the spinorial version of the Weyl tensor, and it decomposes like this given its symmetries, where C is fully symmetric, and its complex conjugates is these objects. So they are complex conjugates in Lorentzian real, for a Lorentzian real metric. Now you can decompose this rank 4 spinor into the products, the symmetrized products of 4 rank 1 spinors up to some scale between the spinors. But okay, you don't care about the scale, you care about the directions. If you take one of them in these complex conjugates, then you get something that you can translate into being a space-time direction. And then you get 4 directions. And these are the so-called 4 principal null directions. Based on these, there is a well-known algebraic classification of spacetimes, originally due to Petrov. So actually even before this story, because you can formulate it in a different way. And the question is, how many of these are aligned? So for type 1, they're all independent. For type 2, 2 of them are aligned. For type D, they are aligned in pairs, so 2, 2. For type 3, 3 of them are aligned. And then there's another one. Type N, they're all aligned. Type O, the Weyl tensor vanishes. For type D, at least this already looks like a kind of double copy, because if you take a rank 2 spinor written like this, then you can write your Weyl spinor in this way. And where would you get such a rank 2 spinor? Well, let's think about gauge theory. We can decompose. So I'm using here different indices just to highlight that this would be a living in Minkowski spacetime. That's how we think about a double copy. Some gravitational solution is a double copy of a gauge theory solution that lives in Minkowski spacetime. The field strength tensor can be written in a spinorial way like this, where this FAB is also symmetric and is the complex conjugate then of this one for a real solution. And you can also consider its principal null directions, completely analogous to the gravity case. Then the Weyl double copy, you can think about writing something like this, where this is just some function which is a proportionality factor. So these type D solutions that I mentioned, they have two principal null directions of multiplicity 2. They are in some sense Coulombic. So this would be like the Schwarzschild solution and some extensions of it, so including rotation, including net charge, as in the Kerr-Taub net solution, including also possibly acceleration. So that's the branch of the symmetric solution. And an important point is that these solutions in vacuum actually have no functional freedom. They only have free parameters, which you can then interpret in specific cases as the mass, the rotation, net charge, acceleration. Now, this story actually matches precisely the Kerr-Schildt double copy story that I mentioned in 4 dimensions for this Kerr-Taub net spacetimes, where the phi we had before, the scalar field, is actually the real part of this S. And there are some extra examples here because it's not symmetric, it's not stationary, but you can still think about it in this way. And it's single copy. Well, the symmetric represents a pair of accelerated, causally disconnected, accelerated black holes accelerating in opposite directions with constant acceleration. And then you have just the analogous solution in gauge theory with the charges. The geometric origin of the possibility of writing this relation is that these vacuum type, these spacetimes admit a killing rank 2 spinner. And this rank 2 spinner can actually be used to construct the Weyl spinner, and then also a Maxwell spinner of a solution that lives on this background, and have a scalar solution to the wave equation that lives on that background. But you can also think about them as living in Minkowski spacetime. They are still solutions. So then you get that the solution in gravity is a double copy of solution of gauge theory in Minkowski spacetime. And indeed, these solutions admit a complex double Kerr-Schildt form. But because it's not stationary, you cannot do exactly the thing I mentioned before, but you can still understand the double copy in this way. Okay. There is also a story for type N spacetimes. So that's another simple example where you think the double copy might be quite easy because there's a single principal null direction, which has multiplicity 4 for in the metric case. So it represents spacetimes with pure gravitational radiation. And there is functional freedom in this case. For instance, well, if you know about PP waves, there are some gravitational version of waves, and yeah, there's some gravitational freedom there. You can choose what profile for the PP wave you want. There is no killing spinner in general. There is for PP waves actually, but not generically. But you can still find a relationship of this type. It's convenient to write it in a spinorial basis, which is aligned with your principal null direction. And then you can prove for vacuum solutions that your Weyl tensor, which you can then, where you can identify a Newman-Penrose scalar psi 4, which is the one that appears for type N, has a counterpart as a Maxwell field, a degenerate Maxwell fields, because it's a null field, such that you have these relations between these Maxwell, between these Newman-Penrose quantities and this scalar, which is also a solution to the wave equation. And there's some non-uniqueness here. You can actually now, because you don't just have free parameters, so it's less restricted. So in a way, type N is less special than type D because you actually have a functional freedom. Okay, so the reason why you can write something like this is that actually these quantities that determine the Weyl tensor, the Weyl spinner, the Maxwell spinner and this S, they all satisfy the same type of equation, the first order differential equation, which is the Bianchi identity for the gravity case at spin 2, the Maxwell equation for spin 1, and the scalar equation for spin 0. It's actually not directly the scalar equation, it's the first order differential equation, but is one which implies the scalar wave equation. The gauge field and the scalar satisfy these equations on the curved backgrounds, for which this is the Weyl tensor. But if you want to think about like a more vanilla double copy interpretation where this field should be living in Minkowski spacetime, then there is a subclass of solutions where you can think about it in this way, the non-twisting solutions. Then there are also solutions on the Minkowski backgrounds. In general, yeah, you know, if you just have some metric, you can't tell that if you can actually separate it from, you know, interpret it as something on top of Minkowski. Yeah, and there is also a twistorial formulation for the Weyl double copy, which is well motivated by this binorial story, and indeed by this integrality condition for the type D solutions, because these stories are intimately connected with twistor theory. You can see Penrose here. Okay, now is this you know, why is this story? Okay, there was this analogy, I guess, with the double copy for sketching amplitudes. But why is this the same thing? Well, you know, in a way, it couldn't be. If you think about Coulomb being the double copy, Schwarzschild being the double copy of Coulomb, you know, there's no other way, just in terms of symmetry, that could not happen. That could happen otherwise. And in the other cases, because of the algebraic symmetries of these spacetimes in terms of their principal null directions, you can think of a similar conclusion. Oh, I see there are some 5 minutes into question time. I see. That was 1 minute ago. I see. Yeah. Okay, so I'll go quickly here. So let's think about the 3-point amplitude of a massive particle emitting a gauge boson, where, so in an amplitude, all these particles are on shell, are on mass shell. Now, these 3-point amplitudes are actually the building blocks of modern on-shell methods for sketching amplitudes, so you can build more complicated amplitudes from them. So they are interesting objects to look at, but they don't exist in a sense. I mean, you know that you can't emit a gauge boson from a massive particle. This cannot be an on-shell process, because if you start at rest, this particle starts at rest, then there's no energy to send any other thing. So there's no support in real kinematics, but they are supported on complex kinematics. And this complex kinematics has been a mainstay of modern on-shell methods. Or you can interpret it also in terms of real kinematics, but on split signature. So if you have a 2-time metric. And this is convenient then to interpret these 3-point sketching amplitudes. And you can take then the classical limits of an amplitude calculation, where basically you have, so this has been much better understood recently. There's an incredible framework put forward by Kozower, maybe, and O'Connell, that is being used in the post-Minkowskian approach, let's say, to study gravitational waves, but also more generally to connect sketching amplitudes to classical physics, where, well, you need to keep in mind that the momentum of a photon, its limit is 0 because of h bar going to 0. What is the finite quantity is the wave number, or the wave vector. Okay, so these 3-point amplitudes compute. What do they compute then in the classical theory? Well, the linearized curvature and field strength. So in this formalism, you consider some observable at a given time, and you think about it as being the vacuum expectation value of something that you have evolved from an in vacuum to with the S matrix. So your observable could be, say, the field strength, and then you do some calculation here, and this becomes, basically, it's kind of on-shell Fourier transform. So there's this on-shell thing here, gives you some quantity which you can actually understand as being related to the Fourier transforms of the Weyl spinner for some solution. So this K, you can decompose it into spinors, and then this would be like the holomorphic spinors and anti-holomorphic spinors, and the the object that appears here, if you're observable, is the Weyl tensor, is the 3-point gravity for the graviton of positive velicity, in this case, to emit, well, to be emitted by a massive particle, or negative velicity for the opposite chirality for these objects. And the same thing for gauge theory, and also an analog for the scalar, where you just get 1/r. So these are understood in this example as an analytic continuation to split signature. Okay, so basically you get that this double copy for sketching amplitudes in this very simple case can be seen to be the same as a double copy as the Weyl double copy, but in on-shell momentum space. So actually it is non-trivial that then you can go to coordinate space and this still works in a very simple formula. And that is actually only possible because the solutions that I mentioned have some powerful symmetry that allows you to do that. In general, you expect a double copy to be non-local in coordinate space. So something like this momentum space, if you go to coordinate space, yeah, it won't look, yeah, it will be a non-local relation. Okay, just in 1 minute, I'll show one slide to show just completely changing topic, just to show another application of the double copy to sketching amplitudes. Well, I told you before that the double copy has its origin in string theory, and it's been underlying huge developments in understanding sketching amplitudes, say in supergravity. On the other hand, sketching amplitudes in superstring theory have really had a very slow progress with time in some directions, at least in the loop expansion. There's been huge progress in other ways, for instance, in having higher multiplicity at low loop and in their algebraic properties. But at least in the loop order, progress has been quite slow. And so one can think about...
Excuse me.
Yeah.
Before you go to string, I have simple questions maybe.
Okay.
Why these linearized gravity programs, at least when you make the perturbation around the flat, around Minkowski, is failed? Can you simply explain me this? What is the main problems to calculate the vacuum to vacuum amplitude using the linearized gravity? Yeah.
The main problem.
Exactly. You start.
So what I was describing is that you can set up a problem in sketching amplitudes of, say, one particle emitting another particle, and then you can associate that to a calculation of the linearized curvature associated with that, which then gives you the linearized curvature of the Schwarzschild solution in the example I mentioned. And you could also get the Kerr solution or get the Taub-Nut solution, depending on the 3-point amplitudes that you consider.
It looks like the asymptotically flat condition is very needed here. Am I right? So I mean, all the example if you have a case, the manifold metric is not asymptotic flat. Yeah, like, so what happened for that?
I did not say that every linearized, that the linearized curvature tensor for any metric can be obtained in this way. I actually don't know the answer to that. Possibly the case, but it could be quite non-trivial. In the case of a stationary solution like Schwarzschild's, then it works in the way that I described. Basically you can have your stationary massive particle. It emits a graviton, but actually in the classical limit, that graviton has zero momentum, so the massive particle is still static.
And I'm sorry, but the last question is that I think you're talking about gravity in 4 dimensions, as I say, because you're talking about the real gravity. Is it possible to? I know that in 4 dimensions you cannot build a good gauge theory for gravity, as we know, but in lower dimensions, for example, in 2 dimensions, then the degree of freedom will be 0. So it's possible to make a toy model. So it could we apply this? Is it any study about the lower dimension of double copy.
You know, studies in order dimensions would need to understand the topological, whether the double copy applies in a sensible way to topological properties. Because, yeah, I mean, this is about propagating degrees of freedom. It's about the double copy of propagating degrees of freedom. So if you go to 3 dimensions, actually there's a degree of freedom in the gauge fields, and then you do double copy and you can interpret it as a dilaton. So in that case, you know, there's no graviton degree of freedom, but your gravity theory still has that degree of freedom of the dilaton.
Thank you.
Thanks. And okay, maybe I'll just then tell you here very briefly about this. So the idea then is to use advances in supergravity that I mentioned before, where you determine the loop integrands using a double copy construction, in particular the BCJ double copy. Then using other recent developments, which are closely related, the ambiguous strings and sketching equations, you can translate this into an expression on a worldsheet, which is not the worldsheet of string theory. It's a kind of field theory worldsheet, where at loop level, you still have genus 0, but with some nodes which represent the loops. But structurally, this is very similar to string theory. So then you can take this expression and try to uplift it to higher genus guided by model invariance. This is it's a non-trivial step. But if you can obtain such an expression, which then has this field theory limit in this degeneration limit that is higher genus surface, then you can hope that this is actually the quantity that is used for the superstring amplitude. And indeed, this is what we propose, and this fits in nicely with superstring amplitudes up to 2 loops. So I'm focusing here on the 4-point type 2 amplitudes. And we present a new conjecture for 3 loops, long after 2-loop case and the 1-loop case. And hopefully this will lead to new developments in helping to understand how to do a first principle calculation that will hopefully confirm this conjecture. Because RNS formalism and also the pure spinor formalism, which has been very useful in recent years, yeah, they face technical challenges when going beyond 2 loops, and then also at higher loops. So you know, we don't know how to define perturbative superstring theory using these formalisms. And on one hand, we may obtain the results in another way. Perhaps this is what we are proposing. But on the other hand, maybe that will also assist us in understanding what's the correct prescription in first principles worldsheet formalisms. Right. Okay. So I told you about the double copy, how it's been very useful and also insightful, applications from supergravity to gravitational waves, superstring amplitudes. And the breadth of these applications is just because this is a structure that is present in all instances of perturbative gauge theory, gravity, and string theory. I've told you about a story of how double copy of classical solutions is possible, and even exact solutions for some special classes of solutions which are algebraically special. So this approach, the algebraic structure, and also stringy aspects. By this I mean this double field theory connection that I discussed. And finally, you can check, at least in simple examples, that this story, that the solutions connected in this way are the same as those connected by scattering amplitudes when you relate scattering amplitudes to classical field quantities. Okay, and thank you.
Thank you very much for this informative talk. We appreciate it very much. I see one hand raised by Dawood Momeni. I don't know if it's from the previous question or if it's a new question. I think it's from a previous question.
Yeah, this is the old one. Yeah, that's the old one. Yes, I'm sorry.
Okay, thanks. So any other questions? Okay, I don't see any. So let's thank Ricardo again for this beautiful talk. And